Hi, Nathaniel. Can you hear me?
I can hear you, Professor.
Okay, great. Thank you. Hey, Derek, how's it going?
Good. How's it going, Professor?
Good, thanks. Great seeing you, hearing you again.
Yeah, it's nice seeing you too. It's been like what, like a year?
Yeah, I think it's been about a year. Yeah. So are you a senior now?
Yeah, this is my last year. I have I think like 7 more units I have to take after this semester, and then I'm done.
Nice, nice.
Yeah, I'm pretty excited about that.
Are you about thinking about what's next?
I'm not sure.
What do you,
I kind of want to, well, I'm going to apply for jobs, and then if I don't get a job, I'll probably get a master's and either pursue embedded systems or something with Verilog, like maybe verification engineering.
okay. I don't think you'll have a hard time getting a job.
Thanks. I hope so. How was your summer, Professor?
What's that?
How was your summer?
It was good. Like very, very inefficient, but I kind of like it that way. I did like absolutely nothing. I did, I like, I'm sort of like, I got one foot in the grave, so I'm like hitting my bucket list items. So I started like getting serious about one of my bucket list items was doing a triathlon.
Wow,
And what's that?
that's impressive. I could never do that.
Well, I don't know if I can either, but I mean like a big one. But anyways, I figured, hey, what the heck? I'm still ambulatory, so might as well give it a try. So I did one on my first one on May 9th. So they have different length triathlons. The shortest one is called a sprint. And like it's a 5K run, 12-mile bike, and like 700 meter swim, and like in a lake or in the ocean. So I did my first one May 9th, and then I was like, okay, I'm gonna need some help. So I got a coach, and then I did my second one in July, so that went a lot better. So now I'm planning to do one end of October, that's like twice the distance. It's like the Olympic distance. And anyway, so I'm like and it takes a lot of work, man. It's like you're working out like 10, 12 hours a week right now, and it's getting more intense. And I don't know if you can tell from a year and a half ago, but I've like gotten 2 shades darker because I'm always in the pool and on the bike or running outside or whatever. So it takes a lot of time. And like after the workouts, you're just kind of like exhausted. And it's like it's really a sport. It's funny. It's like either if you're not a pro at it, it almost feels like a sport for like retirees. Because I have no idea who else would have enough time to be like doing this. So anyway, that's all I did. How about yourself? Did you do anything? Anything fun?
I took 3 summer classes because I had to take the barrel log class because I wasn't able to take it last year. And then I took a network forensics class with Professor Omar. And then I also had an internship at this startup called Trace.
What's the name again?
Trace. So what they do is they like automate. Yeah, they automate soccer clips. So they have a proprietary camera and then these little sensors that players wear. And based on where they are in the field, they have some AI which like tracks them and then captures their best moments and then saves it to an app. So that way they don't have to make like huge highlight reels. So I did like the hardware side.
Oh, it's cool. So is it for like professional soccer teams or is it for like
anyone, high schoolers, college players, professionals? Yeah, pretty cool.
How cool is that? How big was the startup, or is the startup?
Well, it's in Austin, and then also they have an office in Huntington Beach, which is where I go. And as of right now, I think they're close to hitting 5 million in sales. So they're just starting to get a little bit bigger right now.
Nice. That's 5 million. It's great. Wow. You know, where's the revenue coming from? Mostly hardware, or is it like an app? Like
they do subscription based. So teams will subscribe to rent out the case and the cameras for like I think it's like $3,000 a year. And then so we pretty much ship them cases, sensors, and then also tripods and all the necessary things they need. And then that's kind of where all the revenue comes from. And me and another guy that I used to work with when I was a freshman and interning at CalPlug and UCI, we just repair hardware. And then we also diagnose like issues that we see on the boards. We kind of do like quality assurance, but also like maintenance at the same time, as well as sometimes verification, but not as often.
Cool. Wow, sounds really exciting.
Yeah, it's pretty much just a really huge Raspberry Pi project, but yeah, it's pretty interesting.
That's neat. All right, so the founders are in Austin?
Um, I think actually, I know actually the CEO lives in Irvine, but their like biggest office is based out of Austin.
I got it. I got it. I got it. Cool. Wow. That's exciting. I'll check them out.
Okay.
It's a lot of fun. One of the things I started doing earlier this year, I joined the angel investing network down in San Diego, mostly just to like hear company pitches and all that stuff. So it's a lot of fun. You see, you know, they have these things where you have these events like, I don't know, it probably happens once every 2 weeks or once a month, where you just get companies coming and it's like a 30-minute pitch from the founder, Q&A, and then sort of you hear the discussion behind the scenes from the investors. So it's been interesting for me to do that. So it's kind of cool.
That's cool.
Although, yeah, so yeah, it's fun to hear about what other people are doing.
Yeah, I know that at some point my CEO was just like going around Angel's List to try to pick up people to get the startup to like really explode. But like right now we're expanding. We're trying to hire I think maybe one more hardware intern, but I'm not sure yet. They're thinking of a hardware manager at this point, just because like our team is really, really small.
Wow, that's really exciting. And is the background of the CEO, is he a techie or is he a business guy or a soccer player or what is he?
He did business. I don't know exactly what he did, but I know he made a lot of money. I think it was either something with stock or something along those lines at one of those big investor companies. He made a bunch of money and then he ended up quitting and then starting this company.
Very cool. See, actually, while we're so, what's their Trace?
Yeah, Trace.
Youth soccer.
Trace soccer. Yeah.
Trace up. Oh, that's very cool. Academy. Wow. Very cool. Wow. Can't find anything on the management though. Let's see.
If you want to look up the CEO, it's David Lokshin, I think. Lokshin.
David Lokshin?
Yeah, Lokshin.
Lokshin. Trace. Very cool. Seems like a really young guy.
Yeah, he is. I think he's in his like 30s.
Yeah, great. It's a good time to be building a company. Cool. Cool. let's see. I think we're getting close to kicking off here. Okay, guys. I hope everybody's here and we didn't have any confusion. I'm teaching like another class right before this, and I think people got confused with going to the office hours Zoom login. So hopefully we won't have any confusion. So what I was gonna do just today was to go through the go through the syllabus with you guys. Then I was going to give you guys a background of myself, and like sort of how I'm coming to the class, my view of like how to, what I'm going to be looking at teaching you guys. And then I'll talk a little bit about like really at the 30,000 foot level, talking about like what we're going to be covering in the class, and sort of the general approach, because it's going to be maybe a little bit different than some of your other classes. So, we have some limitations about being off campus, and so we got to sort of make do with what we have. Okay, so here's the syllabus for the class. It's on Canvas. I'm going to be recording the lectures and putting them up on YouTube. And usually what I do is I'll have like PowerPoint slides that I'll mark up, I'll annotate as I talk, and I'll have the PowerPoint slides up before the class so you guys can take a look at it. And then I'll have the annotated stuff up also, after the class. So you should have all those things available to you guys. I'm going to try something new this year or this semester. For my office hours, I signed up to this online appointment making app. So that's this second Zoom you guys see in the office hours and office location. So for that one, if you guys go to that website, it's actually from like Squarespace, but like you'll see my available times, and you can schedule in 15-minute increments, from 1 to 14 days in advance for office hours. What else? Let's see. There's a bunch of prerequisites. I'll talk about the learning objectives, and then about the grading. So anyway, we're gonna have 2 midterms and no final. So we'll have the midterm, the second midterm. Usually you schedule it in this class before the finals week, but then, I take a vote, and usually the vote comes in that we should just wait the extra week and have it in final. So it'll be up to you guys about the votes about when we have the second midterm. But the nice thing is, you don't need to worry about a final, like an all-inclusive test. It'll just be each midterm will cover the half of the class that's regarding. And then the design projects is 30%. And that's a tough one because, for us to have, a big part of VLSI design or chip design are the tools. And unfortunately, being off campus, we don't really have access to the tools. So we're just going to do what we can with Spice, et cetera, to like sort of hopefully build a feel for some of the stuff that's in the class. Do you guys have any questions about just the general stuff, syllabus info?
Not as of now. No questions so
Okay.
far.
Okay, sounds good, guys. So let me give you guys first I'll give you guys like my background, just as a way of explaining sort of how I look at the world and why I feel qualified to teach this class with you guys. So I'm not a faculty member at Cal Poly. I'm from the industry. So that's kind of my viewpoint. I think it's really, you guys have a really nice situation in Cal Poly that you have, faculty members that are, this is probably I think this might be my fifth or sixth semester teaching this particular class. But even so, I'm not like a professional teacher in the sense that I really think I've developed a lot of respect for sort of the faculty who are focused on ways to teach and all those kind of things. But so it's good to have that sort of a systematic teaching, step-by-step instructions as you guys are taking, your classes through your getting your bachelor's. But I think it's also good to have people like me from the industry. We have our own way of thinking, our own way of approaching things. I haven't been in school myself. Was like the last time was 1994, a long time ago, is when I got my PhD, and so I'm pretty distant from academia, except teaching these classes at Cal Poly. So I really look at things from a industry standpoint about what's important, what's not. Of course, your academic work is important. I really believe theoretical work is very important, but also practical aspects of what we do. In addition to that, I think that, you guys are all, I don't know if there are any scientists in the room, but for the most part, I believe you guys are engineers, whether computer science, computer engineering, electrical engineering. And to me, I'm an electrical engineer. I think of it as I got my PhD in applied physics, whatever that means, but it's sort of applied, in electrical engineering. But the way I look at engineers is sort of, physicists or whatever, mathematicians, let's say in the case of computer science, that are building actual things. That means it's a really an important part of our work to be aware of business-related issues, like, what's the cost of something you're making? What are the trade-offs? How much time are you using to optimize something? Is it good? When is good enough good enough? When is it time to ship? Then, some of the soft skills. I think in an engineering environment, you guys are going to be in any professional environment. You guys are going to be, a big part of what you'll be doing is selling your ideas. I'm one of those people who believes the core of what we have as engineers, our responsibility and our value added, and what's really going to help you guys progress in your career and enjoy it, is your core technical capability. So that's a given. I'm assuming you guys are going to be graduating from Cal Poly. You guys are going to be technically very good. Once you have that, though, the other part of it, which will really help you guys progress and is necessary in a professional environment, are some of the soft skills. Understanding what your company is doing, where you fit in the role that you're in the company, how does the company fit into the marketplace that you guys are in, what's the value chain, how do you as an individual add value to the company, how does the company add value to the marketplace, and how do you capture the benefits of that value? Okay, how do you monetize that value? I'm not going to go too much into that, but then the other part is like, how do you sell your ideas at work? How do you have presentations, reports that make sense? So, I'll sort of try to touch on a bunch of that stuff as kind of a overlay on our technical discussions. So hopefully you guys will find that interesting. Usually, the students seem to, at least some of them, enjoy that. In the past, I would pick some entrepreneurial or business related topic, talk about that sort of continuously, maybe 15 minutes or something a week as part of the class. This semester, I'm thinking, as interesting as, well, I mean, I find it interesting. I'll talk a little bit about that, but this semester I might actually talk to you guys a little bit more about some of the soft skills that you'll need in your first and second years. I've been looking at that a little bit this summer, like how do you have the good presentation skills, writing skills, those kind of things. So we'll talk about that a little bit. So anyway, so let's sort of just give you guys my background. I went to school at UC San Diego, down in San Diego. Got my PhD there back in the dark ages in '94. And then I came up to, what brought me to LA was I came up and worked for Jet Propulsion Lab, NASA's lab here in Pasadena. Actually, it's funny, I live about a mile from it right now. I could walk over to there. But well, I came up specifically to work on this technology called CMOS image sensor technology, just because it looked really promising, and it ended up being really promising. It was invented in JPL in the early 90s. And then it's the technology that's in the camera, basically in all your cell phones, the camera in your cars, the camera in your PCs, the camera and your, whatever the stuff that shoots Netflix. It all comes from that technology that we built up in the mid 90s. And then my boss at JPL, I think I only worked in JPL for about a year and a half or so. He started a company to commercialize that technology. I joined that technology. That company was sold in 2001, and then me and one of my friends, we started from that company. We started our own startup in 2001. We had a successful exit in 2018, where we sold the company to a Fortune 500 company. And I worked for that Fortune 500 company for a couple of years. And that was just always part of the deal. You got to sort of see that through. And now I'm kind of like retired, I guess, in some ways. I do some consulting work for different companies. I'm part of a investment network down in San Diego, Angel Investment Network, and I teach a couple of classes at Cal Poly. And like I mentioned, I'm not don't have really. I mean, I got a PhD, but besides that, I haven't really been involved in academia. But the reason I'm really teaching is we had employees from backgrounds in Cal Poly, Caltech, USC, UCLA, but we had a really good group. Maybe half the technical team were from Cal Poly over the years, and they really were instrumental in building the company. And so this is, in a small way, my way of sort of giving back to Cal Poly to be involved in, bringing some of those lessons to you guys. Hopefully it'll be useful. So again, because of that, a lot of my emphasis, I've done research over the years, in JPL, I was a scientist, did a lot of chip design myself as a designer, managed chip design projects, Did a lot of marketing, sales. Like I mentioned, I started a company, ran a company for years. And now I see things from kind of an investor point of view, looking at different companies, et cetera. So, for me, like the technical part of what we do is the real North Star. It's really the reason we do what we do. But the business is, I think, just as important because it enables you to do what you want to do technically, and then also to be able to extract value from what you do. Okay, so you don't want to be just producing stuff. You want to be rewarded, whether it's your company, yourself, for what you produce. Like it or not, we live in a capitalist society. That's how things work. You build stuff to get stuff done. You need money. You need money to change hands. You need projects to get funded. You need products to get bought. You need salaries to get paid. So that's all an important part of what we do as professional engineers. Having said that, so I think like from the get-go, what you guys will see is, and I think the interesting thing is when you're doing chip design, VLSI design, a big part of the consideration, as we'll see, there's like sort of 3 or 4 major considerations about what makes a design good. And one of those is cost. It's like a very, very important part of designing and producing a chip right from the get-go. You got to make sure, not just the development cost, but the cost to produce the part is critical. So, you'll see that's something that's in your textbook. It's just right off the bat, something you need to think about. So, so let's talk a little bit about any questions about that, guys?
Nope.
Oh, okay. So, so let's first talk about a little bit about what VLSI is and how it fits into the world. It's been actually kind of a good, we're getting a lot of press lately, which is good and bad. But so you hear about semiconductors in the press, you hear about chips, and all those are really sort of referring to essentially VLSI design or these integrated circuits that we're going to be talking about in this class. So if you look at, there's like several, like maybe like, I don't know what we want to call it, like a perfect storm. There's like a bunch of things that is leading to semiconductors being important now. One of them has to do with just, believe it or not, the sort of strategic, sort of geopolitical issues with the world, power structures with the world. Most of the, especially the high-end semiconductor in the world is being built in Taiwan now, especially the high-end stuff. Anyway, most of it is outside the U.S. And so this has gradually dawned on various U.S. governments and worries about, the semiconductor business being or chips being so critical to everything, from cell phone to, cloud computing to, military electronics, you name it, that this is not in control of the U.S. It's not onshore. Most of it is offshore. Most of it is very close to People's Republic of China, which is now sort of feels like it's kind of getting more in a sort of a threatening environment with the U.S. or disagreements, et cetera, in a risky environment. And also China, the Chinese government has a very big investment and has had a very big investment path or plan to become independent from a semiconductor standpoint and being a leader in semiconductors. And so all that stuff has been very worrying for US governments now. And so you hear about investments, large investments from the US government going into creating or enhancing capabilities in the US for having a domestic supply of semiconductors. So that's the first thing, is just from worries about, from national security kind of standpoint. I was just talking to, I do, like I mentioned, I do consulting for different places. So right now I'm actually doing consulting for a company, a public company that's thinking about buying like a small camera company. And I'm, analyzing the technology, et cetera. So I was on a phone or on Zoom today talking to those guys, and they had just had to, one of the things they had to do is they had to delay a very important project because they had to stop using a chip from a Chinese company. It's called Huawei. I don't know if you guys have heard of it or not. It's in sort of blacklisted by the US government. So they had to stop using that and change to a US-based chip design company for the camera, and that's caused a significant amount of delays, and that's been sort of rippling through the system. So anyway, so national security issues. The second item is that just so many things are that sort of chips. Somebody there's a very famous venture capitalist called Mark Andreessen. You guys may have heard of him or not, but he's famously said software is eating the world, is one of his his important quotes. But all that software is running on chips, and so we're talking about not only are the market growing for chip semiconductors and cell phones. Now there's significant growth in automotive, and not just electric cars, but just the semiconductor content in cars has gone up quite a bit. There's the Internet of Things, these security cameras. It's basically you're getting all this semiconductor content is getting pushed further and further into every aspect of your life. Like my lamp here at my desk, I can adjust it remotely, the intensity of it. So there's a chip in there. There's going to be like basically semiconductors are going to end up in every part of your life, and you may not even notice they're there. So that's also an important part of the semiconductor business. So, I think a lot of things are coming into semiconductors being an important part of what you do. One of the things I'd like to do, let me share my screen. Hopefully I won't share anything. Continue. Let's see. Whiteboard. Are you guys seeing? I'm trying to share.
We're just in the syllabus.
Oh, you're still in the syllabus. Okay. Let me try to pause the Safari. I can't tell what it is. Okay, hopefully it won't be. So you guys don't see any of the embarrassing stuff I look at. No, it's okay. I don't think I have anything embarrassing up. Well, maybe I do. Let's see. This will, okay, there we go. Just kill that. So I might end up with some wrong ones. Let me see. What? What is this thing doing? Sorry guys, I'm trying to share a Safari website with you guys. And Okay, well, that didn't work. Okay, so let me try to open up a Safari page here, which is actually a good intro to the first thing that I have to tell you guys, which is, okay, so this is, are you guys seeing my Wall Street Journal?
Yeah, we can see it.
So this is, okay, good. So guys, this is like, before I go into this, so this is my first suggestion for you guys. Even if you're not interested in anything the Wall Street Journal has to say, just fake it. You'll be interested, just, 2-3 days a week. You don't have to do it every day. If you don't already do it, go through the Wall Street Journal, just read just the front page, read the, articles, what they're talking about. This is you live in a capitalist society. This is the journal of like what's going on in the economy. It does, as you'll see through your life, as you get more and more experience, you'll see how all the stuff a lot of the stuff you're interested in is here. They have there's of course like the home section. Then there is tech. See if I can get in there. Where it talks about the business side of things, like there's a section about Tesla's AI, Facebook, Intel, talking about chips. There's NVIDIA gaming chips drive record quarterly results. Just great stuff. It's really important for you guys to look at that. I suggest that there's no, it's not just for investors. It's not just for business people. It's for professionals, I believe. So it really helps you kind of gradually understand how, whatever you do fits into the overall picture of the economy. But what I wanted to show you guys, I thought it was just a real interesting article that showed up that really said a lot to me. See if I can find it. This I thought, you guys everybody knows Ferrari, but this is like an article from earlier this year where Ferrari, I'm assuming all you guys have heard about Ferrari, like, sexy, luxury, fast cars, Italian cars. They hired a chip industry executive to be their CEO because that's where their business is going. That's where the automotive business is going. They need a semiconductor guy, chip design guy to run Ferrari, not a guy who's into F1 racing, not a guy who's worked for Mercedes or Tesla. No, we're talking about a chip guy. And so I think that says a lot to about where semiconductors are going and how important they are in the overall, not just in the tech business, but in the overall business, overall economy. So anyway, I just wanted to show you guys that. Okay, any questions about any of that, guys? Okay,
no,
so then okay, so great. So let me then talk a little bit about sort of a couple of high level things. One about what we're going to be covering in the class and the philosophy of what we're going to be covering. And then the other one is about sort of a concept that you guys may already be familiar with, but it's a very important part of when I say chip design, VLSI design, IC design, it's all sort of, I use them all interchangeably. So it's an important part of the chip design business, and that's the idea of hierarchy and hierarchically looking at designs. So let's let me see. Let's talk about that first. So this is not just important in chip design, but like you immediately, it's so critical to chip design that like you immediately start seeing it in this business. But it's really part of every other kind of engineering activity that you see, except like a very, very basic thing. And so let's start, thinking about a chip. So a typical semiconductor chip is, made out of a block of silicon. It's, I don't know, it's maybe, let's say we're talking about so let's say we talk about an M1 chip. That's, the new Apple chip. That's, I'm just going to guess it's, maybe, block of silicon that's 10 millimeters by 10 millimeters. Okay. So this thing basically is sitting in your, new laptop from Apple, like new generation MacBook Air or whatever. So, this guy, I'm just going to make up a number, but it's not going to be any less than this. So it's going to have more than 1 billion with a B transistors in it. Okay. And it's going to have a ton of functionality. It's going to have, it probably has, I'm going to guess it, just again, I guess, I'll look this up. Might have probably 20 billion transistors in it. And it's going to have a bunch of crazy interfaces to, I don't know if you guys are familiar with DDR memory interfaces. We might have, interfaces to, Wi-Fi chipsets. It's going to have, display interfaces, whatever, HDMI, whatever, you name it, whatever it is. And so now, you guys I take it you guys have, at least some of you guys maybe have taken classes on designing circuits or transistors or whatever. Some of you guys have, I don't know, maybe not all of you guys. But, there we're talking about, so we're talking about 20 billion transistors. Everything we talk about in this class is based on MOS transistors, which is, we'll talk, hopefully you guys have covered this before. We'll talk about it a little bit, but it's metal oxide silicon type transistors. We won't be talking about bipolar, so we won't be talking about that at all. I only put cross to it, not because I dislike bipolar, I love bipolar, but we won't be talking about it at all in this class in the context of the LSI. So this metal oxide silicon transistor, you guys might have seen it. There's a symbol for it, it's got a complex equation for, current versus voltage characteristics of this thing. There's a whole list of things to actually build it in silicon. We're talking about a, silicon gate. If I look at the cross section, N plus, doping concentrations, blah, blah, blah. Now imagine if you would have to worry about this stuff, and we'll talk about IV curves and all that stuff. If you had to worry about this stuff for every one of these 20 billion transistors, you just couldn't. There's just not enough time. The sun is probably going to burn out before you'll be done designing this chip. Okay, so basically, you have to use a real hierarchical approach the way you design silicon chips, and use the like levels of abstraction, so-called. Okay, so these are both really go together. So if you look at the levels of abstraction in a typical digital product, let's say a cell phone for the sake of discussion. Okay, so at the very high part of degree of abstraction, this is abstraction, hierarchy, however way you want to think about it. I'll call it degree of abstraction. So the highest level, you're talking about, applications running. So this is like stuff you buy from, you know, the App Store or whatever. So those are the applications running a high level of abstraction. Then right underneath there, you might have, let's say, I don't know, iOS, or yeah, I'm not a computer science guy, so I'm just making up stuff. You might have Android or something, whatever, iOS, Android. Okay, so this stuff is probably, I don't know, like, is it Linux? Is it C++? I don't know what this stuff's written in. So, but that's how you would sort of the different degree of abstraction. So, you know, this iOS, I guess you guys can correct me if I'm wrong, is talking to actually like device level interfaces. It has, you know, a link to your camera, or it has a link to your gyroscope to figure out which direction your cell phone's pointed at, etc. So, you know, at the application level, you don't want to be thinking, if you're thinking at the application level, oh, what's like, how do I go down to the system or like actual device level commands for this particular camera chip or for this particular audio chip, etc. You're going to have a hell of a time writing this application. It's going to give you a lot. You need to put in a lot of hours to do that. So what you do is when you're working at the application level, you're several levels of abstraction removed from the device level, and basically your operating system is allowing you to do that. So as we go down here, you know, this device level stuff might be talking to the particular chip that you're talking to, and again, so if you're the operating system, if it needs to know what you don't want it to like have to know the register settings on some chip or something like that. And then the chip is, you know, looking at, say, this would be like a Verilog, or sorry, let me just the first like functional block level abstraction. So again, when this chip, let's say, is, you know, this is what we're talking about, might be 20 billion transistors, sort of in an extreme case. At the chip level, you're talking about, you know, interfaces, whether it's a PCIe interface or a USB interface or whatever, or like you're talking about those kind of things. But then here at the functional level, you're talking about, you know, ALUs, memories, multipliers, I don't know, whatever, things like that. Because again, you don't want to be thinking about these, the device level doesn't want to be thinking about these things, notice, you know, significantly, okay? Next level of abstraction down is going to be like Verilog, say. So somebody went and wrote the code to implement the ALU, or, you know, it might be the actual circuit design. If you're talking about like a memory block or something, that's not written in Verilog, that's actually like designed with circuit elements, etc. Then the next level of abstraction is, so we're looking at, you know, circuits. So these are, you know, AND gates, NAND gates, NOR gates, etc. Next level of abstraction from there is, you know, transistors. I drew some, you know, this would be, as we'll see, this is like the transistor schematic for the poorly drawn one for a NAND gate. And then we're talking about the next level down is the device level, where you're looking at, you know, a MOS transistor with a gate and plus, etc. So basically, to make a 20 billion transistor chip, you've got to be able, you don't want to be thinking about, you know, transistor level things when you're putting the chip together. When you're the person designing this chip, you kind of want to be looking at, you might look at a couple of layers of hierarchy down, or a couple of layers abstraction down, and a couple of layers of hierarchy or abstraction up. You don't want to be thinking about the actual the transistor level things, okay? Unless something breaks, okay? Like the chip comes back, it doesn't work. So, these guys are wondering what the hell happened, and you might find out that something bad happened to a particular transistor. It had a electrostatic discharge event, or we'll talk about that a little bit. But in the course of a design, the idea is you work on a level of abstraction, only a few levels of abstraction at a time. Okay, otherwise it's just too big of a problem to solve. These things are just way too complicated now to be digging into the roots of each component for most everything, but certainly in chip design. So this class we're going to be focused on mostly on the circuit level. Okay, so we're going to be looking at the circuit level, so that means we'll also be working somewhat at the transistor level and somewhat at the block level. So this is kind of the degree of abstraction in this class. But like I was talking to Derek, he's taken, was taking Verilog this summer, so that's also can be a part of chip design, but it's essentially a Verilog is one level of abstraction above what we're going to be talking about in this class. And then some of you guys, maybe with doing electrical engineering, etc., you were maybe taking device physics classes, and that's one level of abstraction below what we're talking about in this class. So anyway, this is like really, really a powerful concept. It probably makes sense to you guys, but you won't get a feel for how powerful and how it's necessary. It's not even a critical concept. It's absolutely necessary for us to be able to build the things with the level of complexity that we build at the moment. I don't care if it's I'm just guessing that it is the case in all aspects of electrical engineering, computer science, etc. You just have to use degrees of abstraction, the way you look at different aspects of your design, how your piece of the design interfaces with different things, how it fits in, and that kind of thing. So that's one of the key elements. We're probably gonna look at this a little bit more, but when you look at the context of this class, I think it's really important to think that this is where we are. This is sort of circuits, transistors, and some block level things like ALUs and IOs and those kind of things. That's what we're going to be talking about. And then some of the other classes you might have taken, I think you guys have like probably a microprocessor design class. You guys will be, that's sort of at this level of hierarchy. So you kind of see how things fit it. So, okay, so that's hierarchy and degrees of abstraction. Second thing I wanted to talk about is the way we approach looking at VLSI design in this class. So depending on what you're doing at a particular level in the design in VLSI, and sort of like looking at the blind people feeling an elephant, and each one has a different description of the act. So if you'd like to talk to chip designers, they might see VLSI design in a bunch of different ways. So some people see it as like Verilog design, sort of going back to this hierarchy. So they're doing Verilog design. They are basically synthesizing from their Verilog and creating circuit level stuff. So this is sort of like they live in a sort of computer, almost entirely like a computer-aided design tool world. So they just see things as like, and like also, like database management. So plus database management. So what you'll see these guys doing is they may be writing Verilog, they may be creating scripts, they're doing verification tasks to make sure everything fits together, and that's their world. Then, you know, another group of people might actually be doing circuit design because sort of on critical, let's say, critical data paths that are going very fast. So very, you know, whatever is like critical and going very fast or very low power or something like that, or they might be creating like memory elements. So they might be making random access memory. They might be making specialty IO, like high-speed IO, those kind of things. So these guys look at things from a circuit design perspective, but they also use computer-aided design tools, but more sort of closer to SPICE and all those kind of things. So, so one of the issues we have in this class is it's because of COVID, because the way the class is set up, it's very hard for us. Basically, we can't do this part. We don't have, in a remote sense, we don't have access to these tools. You know, Cal Poly has the tools on campus, but you know, doesn't at the moment doesn't have IT support, and you don't have to be on lab to use it or on Cal Poly to use it. So we're kind of reduced to this part of, you know, that's where labs are going to be like simulation based. We're going to be looking at sort of circuit designs and those kind of things. Okay, so that's one. The second thing is that there's actually, when you look at the phases of doing a design, a chip design takes, you know, somewhere between, so the design part of so chip design cycle. We'll probably talk a little bit more about this in the first class. So it might be about, I don't know, like 6 to 12 months of actual design. And this could take anywhere between 5 and, I don't know, 50 chip designers. And a bunch of expensive computer-aided design tools, etc. By the way, chip designers make good money. So this means this is kind of an expensive proposition. So just the design, let's say that costs somewhere between $2 and $200 million. Okay, depending on whether you have 50 designers or 5. Basically, it's like degree of complexity. And you know, depending on what you're designing, are you designing a microcontroller? That might be more like, you know, a couple $1 million. If you're designing the next, you know, Qualcomm baseband chip, it's 200 million. Okay, and that takes 6 to 12 months to design it. Then you're gonna go get it, put it into a manufacturing plant. And that might take anywhere between, say, it's typically 3 to 6 months, depending on how impacted the fab is. And that also might cost you somewhere between, I don't know, like 500K to, I don't know, 50 million, say, to get it produced. And now you can test this and see if it works. You know, this is like 18 months later, 24 months later, so you're sitting here 24 months later. And you've already spent somewhere between 2.5 million to, I don't know, say 300 million to get here. And so now you can test it, you can give it to your customers. Hey, does this work? Do you want to buy it? Whatever. So one, this is a very expensive process to get to that point. And it's like very different than a lot of things you guys have seen, because it's not like you can just change the code, compile it, change the code, compile it, see if it works. have a bunch of applications guys seeing if it runs on the operating system. I'm not sure how software flow works for getting the product out. It's like a very long, expensive period of time, and you've already spent a lot of money, and then you get an indication that all that money was well spent or not. Maybe it's kind of like launching a space probe or something. After spending all the money and all that stuff, you'll see when it launches what'll blow up or makes it to the atmosphere. I don't know how you guys want to look at it. But this means two things. One of them is each one of these steps is really an expensive step. By the way, we're talking about these are just your costs, okay? These are like salaries you're paying, money you're paying to the vendors, et cetera, that we're talking about. we're not even gonna talk about the opportunity lost if this thing comes late. Like if this doesn't work and it takes another 8 months to make this chip, you've lost a huge amount of revenue, lost a huge amount of income from this market. Because imagine if you're making the next generation cell phone and everybody else's cell phone comes to the market and yours ends up being 12 months late. Well, a bunch of people aren't going to wait for you to come up with your cell phone. They would have bought the cell phone they wanted, and you're just going to lose a huge amount of revenue if you're late. So again, if one thing is to just out of money pocket, but then the amount of revenue and profit you make off of this part for being late is like a huge problem if you got issues with it being late. Okay, so what does all this mean? This means that it behooves you to, at each one of these steps, think through what's about to come in as much as you can. You don't want to start this 6 to 12 month process and $100 of million process potentially, or a very expensive process, and find out even 25% through that, look, I'm going down like a wrong path here. Like this approach that I'm taking with this thing is going to make the chip $100 more expensive than I thought, and the customers aren't going to pay for that. So that's like a no-go. Or the power consumption is going to be too high, or something like that. You want to find that out before you start. You want to do as much as you can ahead of time when you start to make sure you're starting on the right path. And then once you're on this path, then we're talking about you're continuously doing these things and you're continuously double checking whether you're on the right path, etc. So again, if you find that out when you're here, that, oh crap, like I made the wrong design choices, that either this chip's not going to be fast enough, or just talk about some signal path in the chip, some critical signal path in this chip is not fast enough, there's too much power consumption or too big, whatever. This is the wrong time to do it, right? You've already way down the path, and you're talking about disaster at any one of these points. And you find out you've got the wrong path, and the further you go, the more expensive it is. So a lot of the stuff we're going to be talking about in this class is methodologies up front, okay, to estimate, to figure out how fast some particular circuits are going to run, how the physical size of some circuits, power consumption. So basically to look at the design at a simplified, you could say back of the envelope, it's more like an Excel level look at optimizing these circuits, etc., to figure out ahead of time, are you going down the right path, or do you need to at this point tell your CEO or your manager, like, hey, look, we got to talk to the marketing guys. We're not going to be able to meet the spec. Is do we have a fallback position, or hey, we need to get rid of this particular function to meet our area requirements, or we need to find another manufacturing partner, those kind of things. So a lot of the stuff that we're talking about in the class is, one, getting an overview of what a VLSI design looks like, but also like these Excel-based hand estimation models, etc., to make sure you're on the right path. And, coincidentally, the nice thing about that is it gives you guys a overview of what the whole sort of design, the whole cycle sort of looks like, hopefully. Okay, guys, so that was kind of a real long-winded thing, probably talk more than I keep you guys more than I wanted to in this first lecture, but I just wanted to give you guys those ideas about the class. Hopefully it makes sense, so you guys can get a feel for about why we do certain things in the class, and so how it fits into a bigger picture. Hey guys, any questions about any of that?
No questions so far.
Sorry, what's that?
All right, no questions.
Okay. Okay, guys. Well, if no questions, I'll let you guys go.
Thank you, Professor.
Yeah. Okay. Thanks, guys. Take care.
Ask a question real quick.
Yeah. What's up?
So with the textbook, like, where do you want us to start off at?
You mean in terms of like reading it and all that stuff?
Yeah.
I would just hold off on like reading. I'm gonna put the view graphs on, and good question. I'll give you guys I'll start giving you guys a reading list.
All right, thanks.
I'll start putting them up on a weekly basis. Okay. Anything else, guys? No? Going once, going twice?
I think it's
Okay, guys.
Thank you, Professor.
Thank you,
Thanks.
Professor.
Have a great weekend.
You
Thanks.
too.
Bye.